Cool. All right, Alex.
Alrighty. So, yes, hello, welcome back. Second part of this kind of foray into my attempt at trying to distill some of the cool ideas that I was exposed to in a course that I took as an undergraduate called Order of Magnitude Physics. The lectures are, or the slides are available here. It's sort of part of the same slide deck as the first time. I created a problem set of some fun problems to kind of work through for you to kind of try or talk with others and stuff. And I will prepare a solution set sort of by next week that I'll kind of upload and share in the chat room. And if you haven't joined it already, here's the chat room for Brainiversity generally that we could use to talk about the problems, or if you have any questions or anything. Okay, so I wanted to start by just sort of like recapping some of the things we talked about last time, maybe kind of give some, perspective and revisit some of the same ideas. So overall, if you are intrigued by some of these ideas and really sort of want to dive in deeper, for the most part, a lot of the example problems and a lot of the things I'm talking about, I'm cribbing from Sanjoy Mahajan, and he's got 2 books that are open access from MIT Press that kind of go into a lot more detail, go a lot slower, and talk about some of these techniques sort of more generally, and also sort of like gives an overview of sort of basic fixes and stuff. And I think they're really, really neat books, and I encourage anyone to kind of check them out. And I will be continuing to kind of crib from them for ideas as we go on, most like the example problems and stuff, for the most part, I took from these books. Okay, so to recap, last time I tried to talk about dimensional analysis and introduce it and talk about units and stuff, and just to kind of very quickly recap, units, feet and meters and things like that provide some kind of context. You can think of it as offering some a way of comparing 2 quantities. When I measure my height in feet, I'm comparing my height to the height of some specific stick that we all share. And that allows you to kind of reason about how tall I am without having to see me, as long as you have a similarly sized stick. The difference between units and dimensions are a sort of experience. Feet and meters are different units, but they're both units for the same dimension, which is length, a sort of spatial extent. And that's distinct from other types of measurements that we make in the world, like temporal extent, like time, or temperature, or mass, or things like that. And the kind of, the fundamental point was, since the world doesn't sort of care about our description of our own experiences, the universe doesn't kind of care about us, all formulas in physics have to be sort of dimensionally consistent. They have to be invariant to any change of units. And that means that the formulas have to be dimensionally consistent. You can only add quantities, you can only add lengths to lengths, or masses to masses. Both sides of every equation and all terms in every sum all have to have the same dimensions. And this places an extreme constraint on the complexity of formulas that you are sort of allowed to write down between physical quantities. And the kind of central result that we kind of talked through is called the Buckingham pi theorem. And the kind of simple result is, if I try to express some formula in n physical quantities that are written in k independent dimensions, there are only n minus k independent dimensionless constants that I can form. And this sort of immediately allows me to reduce the potential complexity of any formula that I might be interested in, and sometimes can very magically reduce the complexity entirely. And we worked some examples. One of the examples I think we worked on last time that we'll revisit now is we talked a little bit about how air drag works. And I guess maybe something that I didn't emphasize is, let's say you weren't going to do sort of dimensional analysis, or let's say you weren't going to do this kind of simplified stuff. If you really wanted the right answer, if you really wanted to do the physics, what would that mean? Well, for something like air resistance, that means trying to solve this equation. This is the Navier-Stokes equation. This is fluid flow, and it's a very hard equation to solve. In fact, one of the Millennium problems, right? One of these math problems that has $1 million prize, is trying to prove that this equation has unique solutions. and it remains sort of an open question. So I guess at the center, it's very easy to kind of get lost when trying to solve a problem, and it's sort of, you can very quickly run into a brick wall where things are sort of impossible and there's no hope to be had. And like, if nothing else, the kind of lesson of Sanjoy's books and the sort of order of magnitude physics class, and the lesson that I'm trying to teach you is try to be audacious and just sort of make very quick and loose approximations that can often kind of like, open the dam, let everything flow, and you can usually get within spitting distance of a decent answer without having to worry about all of the details, which are often very overwhelming. So in particular for drag, if we wanted to try to figure it out, let's say we were interested in the force caused by drag. To kind of remind you how the dimensional analysis works, we kind of start writing down physical quantities that we think might be involved. And we're interested in finding a force, which I'll call F. We think it might depend, we're moving through air, so it's going to depend on some quantity associated with the air. We'll write down the air density, which is, as I move through the air, it depends on the size of the object, and we'll represent that with the area just because we'll make it simple that way. And we feel as though it's going to depend on the speed at which we move through the air. So if we just, now we have a question, right? Given these four physical quantities, what sort of function can exist between them? And this is where we get to sort of use dimensional analysis. A priori, like, without any knowledge or without any constraints or without any knowledge of, how dimensions work and stuff, it seems like there could be an arbitrarily complicated function relating these four variables, right? Some four-dimensional nonlinear function that could take some ridiculous form. But because, again, the universe doesn't care about our sort of description of things, we know that the formula has to be dimensionally consistent, and we know that that places a huge constraint. And in this case, with four physical quantities measured in three independent dimensions. What are the three independent dimensions here? We can, I guess, talk about them. So what is a velocity, right? A velocity is a speed. It's a length that you go in a certain amount of time. So its dimension is length per time. So length and time are sort of independent dimensions. They are independent experiences that we sort of have in the world. An area is a squared length, but that length is the same sort of length as associated with velocity, right? When I measure the size of an object, the spatial extent of the object is related to the spatial extent that I traverse when something moves quickly. But here, length and time are distinct. What's the density of air? So it's a density. So that's if I make a box of air of a certain size, of a certain volume, L cubed, it will have some mass. And mass is yet a distinct dimension. Density has dimensions of mass per volume. And a force, what is a force? You might not know, but hopefully, if you remember, any formula from physics that you've ever heard, we can rely on the fact that physics is dimensionally consistent. So maybe you remember like F equals ma. And if you remember F equals ma, then you can figure out the dimensions of force. Force is a mass times an acceleration. It's a mass times an acceleration. An acceleration is a speed per, a distance per second per second. So four physical quantities in three independent dimensions, mass, length, and time. Buckingham pi tells us that 4 minus 3 is 1. There can only be one dimensionless combination, independent dimensionless combination of these four variables that we can form. And so we can kind of look at it, and more or less by inspection, I think we can work it out, right? You start with the force, we need to get rid of the mass. To get rid of the mass, you divide by the density. Once you divide by the density, we have something that's L to the fourth per t squared. To get rid of that, to get rid of the t's, we're going to use a v squared. And then we have two lengths left over, and that's an area. And so hopefully that checks out. And so what have we done? We could have had some arbitrarily complicated formula between these four physical quantities. Buckingham pi tells us there's only one independent combination that we can form. Once we found an independent combination, we'll call this pi. We know that any physical formula involving these four quantities has to take this form. It has to be a function of this pi. It could be an arbitrarily nonlinear function of this pi, but it has to be a function of pi. It can't be an independent function of the f and the rho and the a and the v. But this is a huge restriction, right? Because sort of regardless of what this formula is, because in physics everything is nice and invertible, we should be able to like invert the formula and write this as pi as the inverse of 0, right? The image of 0 under this function, whatever it is. And whatever that is, that's just going to be a number. And so without like the fact that nature doesn't care about the way that we measure things, the fact that these 4 physical quantities are measured in 3 independent dimensions, 3 sort of independent ways of experiencing the world, means that they have to be related. And in total, all we can say is that this pi has to equal some number, some pure dimensionless number. It might be 4.3, it might be 1.6, but that's sort of all that we're allowed to do, the only kind of relationship that can exist between these 4 physical quantities. So in this particular case, we can then, set it equal to a constant and sort of solve, and we discover that the force has to be some constant, a number, pure number, times rho times a times v squared. And I don't know if you may have seen it before, or something you might remember from in the past, but if you take a physics class, they'll teach you that the air resistance takes this form. They kind of reparameterize the constant as the coefficient of drag, CD, and they put in a factor of a half for reasons. I think it's because they want it to look like 1/2 mv squared, and rho is kind of like an m.
Yeah.
But yeah, so like I guess like usually in like a physics class they'll tell you that drag takes this form, but maybe you might not have appreciated is it can't take any other form. If you're going to have only these 4 physical constants, it can't be a cubed, it can't be square root of a, it can't depend on a velocity cubed or a velocity. If the only things that are allowed to be in there are density, area, velocity, and force, it has to take this form. And the only thing that can change is a coefficient, a constant. So that's neat, and that's sort of what we talked about dimensional analysis. It can put a huge constraint on the complexity of formulas, and it can often kind of like magically solve things up to a constant. But it isn't very informative, right? Like you kind of turn the crank, you kind of manipulate some symbols, and it doesn't give you a lot of understanding. So the other thing that I tried to introduce is this idea of like doing twiddle reasoning. So trying to kind of actually think through equations, but not worrying about any of the factors, not worrying about any of the signs or anything, as a way of trying to build understanding for the quantities and the relationships. And these work in concert. A lot of times, if I'm trying to figure out a problem, I'll kind of start by doing dimensional analysis, as it's like a crank that I can turn. I'll end up forming some dimensionless factors, and then I'll try to like look at them and see if I can understand or come up with a story for why those quantities might combine together in that sort of way. And we can do that for air resistance. We can tell a story for why it should take this form, maybe after we find it. And the simple kind of story we can tell is what we can try to understand or get a better understanding where this comes from. We can tell one of these sort of twiddle stories. Oh, where does air drag come from? You feel air drag because you're moving through air, and you feel a force because you have to push the air out of the way. And we can kind of like estimate what the contribution would be there. We know that force goes like mass times acceleration. Maybe you've seen before, it's also a time derivative of the momentum. Momentum is mass times velocity, so the derivative of mass times velocity, constant mass is mass times acceleration. In either case, we can, when we're doing twiddle reasoning, we can approximate derivatives by just differences, take finite differences. It's a change in momentum over a change in time. What's changing the momentum? How do you change the momentum of an object when it moves through air? It's because you have to push all the air. So the momentum change, the mv that we vary, is going to be the mass of all the air that we trace out. And the air that we trace out is going to be all the air in sort of like a cylinder. If I move some distance delta x, density times area times delta x, the density of air times this volume of the cylinder is going to be the total mass of air that I have to move. And what speed do I need to, it's sort of sitting still in the air. What speed do I have to raise it to? V, the velocity of the object that I'm moving. I have to, speed up the air. Mass times V divided by delta T. Delta X over delta T is another way in twiddle world of writing V, right? A change in distance over a change in length. And so we can tell this kind of story. Now we can, the dimensional analysis told us that these 4 physical quantities, the only form that they could take had to be the form that we found. But now, looking at it and kind of thinking about it, we can tell a story about why this is. Why does it take this form? Why does it go like v squared? Because you get one term from the momentum you have to add to the air that you're pushing out of the way, and you have another term which the other velocity comes from the fact that the amount of air that you push out of the way is proportional to your velocity. As you go faster, you have to push more air out of the way. And we can kind of like, by looking at the story, we can understand why is it linear in the area? Because the amount of air that you push out is linear in the area. Why is it quadratic in the velocity? For the reason we just said. Why is it linear in the density of air? Because the mass of the air that you push out of the way is linear in the density of the air. So these really go in concert, and you should sort of like, maybe try to reason problems both ways. Okay, so that was sort of like a recap. Let's keep going now. So let's talk about some new problems. Let's talk about some old problems, and let's talk about other ways that you can kind of reason about problems. So we talked about sort of dimensional analysis and sort of twiddle reasoning. Now let's take another step. So I want you to take a look at this question, right? So let's say I've got a triangle, and I draw a line through an equilateral triangle of some length, and I'm interested in what is the length. I'm trying to draw a cut at some height such that I bisect the area. If I was going to cut the area exactly in half so that this bottom region has exactly the same area as this top region, what would the length of that line be? And I'll actually kind of let everyone kind of ruminate about that a little bit.
Isn't it 1 over square root 2 of the original length?
Exactly. So if I was being honest, what would I do? If you caught me on most days, I think I would make I think I would solve this the way most like high schoolers would solve this, right? I would actually start like drawing little diagrams, doing out the thing, and try to figure out the area of this triangle. It's an equilateral triangle. It's going to depend on the base times the height, and then I need to get this height, and I do a little bit of geometry to figure out that this is like the square root 3 or something, and I have to equate the areas and solve an equation. But hey, I mean, the fact Ajay got it so fast means he didn't do that. And there's a much quicker way to solve this, which is just to rely on sort of scaling. We know that area is proportional to a length squared, right? Area is a squared length. And so given that proportionality, we don't have to do any work. We know that if area goes like length squared, then in order to have the area, the length has to go down by a factor of square root 2. And you're done. That's it. And that brings us to the kind of next, the thing I want to talk about, scaling, which is sort of one level beyond twiddling. Dimensional analysis was kind of, working the math, looking at constraints between physical quantities based on the dimension. The twiddle analysis was trying to like equate things up to a dimensionless constant. Scaling is sort of ignoring everything and only focusing on one dependence. So here's another question. This actually shows up on the PISA exam, which they use to sort of test how well schools work for internationally, different countries. One of the questions they asked was, you have a 40 centimeter pizza that costs 40 Zeds, some made up currency, or a 30 centimeter pizza that costs 30 Zeds, which is the better deal? And American students do terribly on this question. The ones that do well do it by working out, writing down the formula for the area of a circle, sticking in, 40 centimeters, dividing the area of the pizza, divided by the money for both things, equating the two, working out all the math with the factor of pi in their calculator, and saying which is the best. But the point is, you don't have to do any of that, right? We know that area goes like length squared, so the deal that you're getting here, the amount of pizza per money, is going to go like length squared over money. 40 squared over 40 is 40. 30 squared over 30 is 30. So the 40 centimeter 40 Z pizza is a better deal because 40 is bigger than 30. You don't have to do any work. And this works, it might make sense. And I think, the American students can solve that problem because they do remember the formula for the area of a circle. But if you change it so that you ask them about the deal on these two calzones, they're completely lost because they don't know the formula for the area of a calzone. But of course it doesn't matter because area is proportional to length squared. It doesn't matter what the sort of shape of the underlying object is. You can solve this just as easily. So scaling is very powerful, and it lets us answer questions sort of very quickly. Now that we have some understanding of air drag, this is something that we can immediately answer. How much more gas do you burn going 5 miles an hour faster down the highway? And
something on the order of the square root of the.
Yeah, so the one the thing that we can use scaling. So we know that the force went like v squared, energy goes like force times the distance, so the energy that you go in some fixed distance is going to go like v squared. And we just know the fact that the energy is quadratic to the velocity, and we can use that to kind of solve the problem. Now, you might set up the proportionality exactly, but there's one more kind of thing that I want to show you, which is once you reduce something to a proportionality that, it means that given any two instances of the problem, you can kind of solve it, right? You can set up the ratio, and all of those factors that you dropped cancel out exactly, and you can kind of solve for a proportional relationship if you know how things scale. So if all you can get is figure out the exponent on the variable of interest, then if you knew one other instance of the problem, you'd be able to kind of work everything out. But you can usually go, one more fact that's useful is if you have a scaling relationship, so if you have any y that goes like x to the n, if we look at the derivative of this function, it takes a very simple form. dy goes as n x to the n minus 1 dx, which you can solve that as a factor of y and a factor of x in it. You can kind of see this down here. If y goes as some constant times x to the n, we take a derivative. dy dx is n a x to the n over x. That's the way I'm writing x to the n minus 1. And if you solve this, you'll notice that dy dx is n y over x. That's the same as dy over y is n dx over x. This is a very useful sort of low entropy way to remember the derivative of a power law. Because what is it telling us? It's telling us that if y goes as x to the n, a fractional change in y is just n times a fractional change in x. And that works for any power law. And so assuming that we have small changes, we can just kind of like multiply those changes by whatever power we have. So going back to our highway question, if we're going 5 miles an hour fast on the highway, because we know that energy goes as v squared, the fractional change in the energy is just 2 times the fractional change in the velocity. If we change our speed by 5 miles an hour out of 60, that's 1/12. That's 8%. 2 times 8% is 16%. Use 16% more fuel going 5 miles an hour faster on the highway at 60 miles an hour. That's why back in the day, the federal speed limits were set at 55 miles an hour. Originally, it was a fuel cost saving, fuel saving measure back when we had the oil embargoes in the 70s. The focus is scaling. So either by doing dimensional analysis or by doing this sort of twiddle analysis, oftentimes we can very quickly figure out how things depend just as a power. And once we do that, not only could we sort of solve arbitrarily, we could scale things from one instance to another if we happen to know some example of the problem or some other instance or at some limit. But for small changes, we can sort of immediately estimate how things change. Very powerful way of estimating small changes. Okay, so we talked about air drag, and maybe you've seen that before, but I think it's or maybe you haven't. But I said that nature requires that if there's going to be any relationship between these 4 things, it has to take that form. But now let's just sort of like verify, because I think it would be fun. So I also got this from Sanjoy. He puts it in his books and talks. But he has these cutouts for these cones, and one cone is twice the size of the other. If you cut these cones out and you tape them together, you get these nice cones. So here's the small cone, and here's the large cone. And now the question is, I'm going to step back here, and I'm going to drop both of these cones from kind of above. Question is, which is going to fall faster than the other? Is the big cone going to fall faster than the little cone? Are they going to fall about the same, or is the little cone going to fall faster than the big cone? So I want you all to think about that. I step back here.
I would like to guess that they both fall at the same time.
Okay. Why do you guess that? You wanna-
Because there's no time dimension anywhere in their other description, right? So
All right. So, I mean, and maybe you guessed that for another reason, right? In physics class, one of the things they sort of beat you over the head with is that all objects kind of fall at the same rate, right? So, well, we don't have to guess, we can test. So here, I'll drop them. Count of 3. 1, 2, 3. And we'll do it again to kind of get some experimental noise here. So I don't know if hopefully you can see when it hit, but I guess to my eye, it seems like up to experimental error, those land at the sort of same time.
yeah,
But maybe to test out one more thing. So Padang, what I heard you say is there was no time there, so that they should fall at the same rate. Now here I've actually got 4 of the large cones, and I'm going to stack the 4 large cones together, and now I'm going to drop the 4 large cones and the small cone. Do you think that these are going to fall at the same rate?
good question.
Shouldn't. All right.
I'll have to, yeah, still stick to the dimension analysis. Yeah.
We'll drop these. Ready? 1, 2, 3.
Yeah.
And to me, it seems like the 4 cones are definitely falling faster now. And I think I could even say that they're probably roughly twice as fast. And I think I could probably race them against each other, one sort of twice the height of the other. Get them to land at the same time. So I just think that was a sort of a neat way to. What we can do now is we could actually validate that we know the answer here. So we worked out how drag works, and in this case, when these things fall, they're not really accelerating; they're falling at a constant rate because they're very light objects. So they're falling at their terminal velocity, and so we can work everything out. The fact that they're falling at their terminal velocity means that all their forces balance. Gravity is pulling them down, that's mg. Drag force is pushing them up, that's the force of drag. And if we do our sort of twiddle analysis, we know how the drag force goes. Drag force goes like rho a v squared. That's what we did twice. We equate that with mg, and the mass of these paper cones, they're both the small and the large cone are made out of paper, so they have the same sort of surface density. So their mass is just scales as their area. So what we get here is that rho a v squared goes as like sigma, the mass density, the weight of the paper, times the area times g. And now you'll notice that v squared, the a's cancel, and their velocity, their terminal velocity should be independent of their area, which is sort of what we saw. At the same time, it's not so simple that all objects fall at the same rate, the thing that they actually teach you at school, because if we stack 4 of the cones, now they don't fall at the same rate. They don't fall at the same rate, even though the area is the same. The density, surface density, right? The mass density is 4 times larger. And if the density is 4 times larger, the velocity is 2 times larger. And so hopefully you can take this as some sort of experimental evidence that our formula works because the scaling worked and it was able to, our formula sort of correctly predicts the result of the experiment. I said all that, but one of the other things that we tried to talk about and something I want to focus on is how dimensional analysis can sometimes fail. So go ahead.
Good question. So the velocity should go square root of the density, basically. So if you increase the mass 4 times, then we should kind of get basically like half the velocity, or half the velocity, terminal velocity.
If the density goes up 4 times, the velocity should go up 2 times.
Got it. Okay.
And
Good.
that's
Yeah,
what
that makes sense. Yeah.
Okay, so how do these things fail? They fail if you sort of don't know which physical constants to kind of put in there, or if you sort of forget some. So I don't know how much sort of physics you remember, but one thing you might complain about is, hey, what if we put like viscosity in there, right? Viscosity is a physical property of fluids. It has to do with sort of how thick, how viscous they are, viscosity. What if we included viscosity? It seems like viscosity should have something to do with drag. And I mean, on the one hand, you'd be right. Viscosity has a lot to do with drag. So what happens if we go back and we try to do our dimensional analysis, but we put another physical constant in there, viscosity? Maybe you don't know, but you could look up. Viscosity has dimensions, and it has dimensions. This is a kinematic viscosity. Has dimensions of a sort of area per time. Now, Buckingham Pi says we've got 5 variables, 5 quantities in 3 dimensions. There should be 2 dimensionless constants. So we have the dimensionless constant we had before, but there should be a new one that is independent of that. The fact that we added a viscosity means that, to get an independent quantity, we need to find a dimensionless constant involving that quantity. If viscosity is L squared per T, we need to kind of get rid of an area at a time, and we can get rid of it with the velocity times time. I'm sorry, the dynamic viscosity here is new and velocity is V, and they look similar, but that's what everyone uses for those 2 things. Can help it. So, okay, so if we had done the dimensional analysis, but we had included the viscosity, which seems like it's a physical quantity that should matter, then dimensional analysis doesn't give us an answer. It instead says that we still get most of the scaling. We still say that the force should go as rho times the area times the velocity squared, but now it could be times an arbitrary function of this other dimensionless constant. And we didn't have that there before. And like, why not? And in fact, not only did we not have that there before, but I just did an experiment to try to convince you that all of the scaling on this side was correct. While we dropped 2 cones that differed by a factor of 2 in their radius. So even though this thing went up by a factor of 2, we observed that they sort of fell at the same rate, which suggests that whatever that this function was behaving like a constant. Now, one of the things I wanted to talk about is that we can usually see evidence of that. If we do dimensional analysis and we have extra constants in there, if we evaluate the values that the constant take, we can sometimes get a sense of whether they're important or not. So in this particular case, what we need to know what the viscosity is. I guess if you're not familiar with viscosity, it really is just how viscous a thing is. Here's a simulation from Wikipedia of a very non-viscous liquid like water and a viscous liquid like honey. Right? The honey kind of behaves as if it's thicker. In terms of the physics, what you can imagine is if you had like 2 plates with the fluid between it, and you tried to drag one of the plates to the left, the viscosity is sort of a measure of how much of that force would transfer to the top plate. Sort of how much technically the kinematic viscosity has dimensions of an area per time. It's a measure of how quickly the momentum diffuses through the fluid. It's a diffusion constant for momentum. But none of this really matters. At the present, what I want you to just know is viscosity is another physical quantity. It has some dimensions, and if we had included in the dimensional analysis, it should have been this whole other scaling that we sort of didn't observe. But I want to tell you that we might have expected that. If we actually plug in some numbers here, so you open up some thing or you look on Wikipedia and you look up the kinematic viscosity for air, you discover that air has a kinematic viscosity of 1.5 × 10⁻⁵ meters squared per second. And for our like smaller cone, it's falling at something like a meter per second, and it has about a 2 centimeter radius. This dimensionless constant, which happens to be called the Reynolds number, which you may or may not have heard of, but it's a dimensionless constant that has to do with fluid flow. For this cone, it was like 1,300. And that's a big number. And the other lesson is that these dimensionless functions in physics, when the arguments tend to be either very big or very small, the behavior tends to be very simple. And in our case, we actually dropped the small cone and the big cone. They differ, their radius differed by a factor of 2. So the small cone had a Reynolds number of about 1,300. The big cone had a Reynolds number of about 2,600. That's a big difference, but it had sort of no effect on their terminal velocities. And so that is experimental evidence that this function between 1,300 and 2,600 was basically a constant. Now, dimensional analysis can't tell us what that function is. When we actually plug in some numbers, we might expect that the behavior is sort of simple or like a constant if the values are very big like they are in this case. But dimensional analysis is never going to tell you what that function is. You have to sort of do something else. But still, if we do the dimensional analysis, we had 5 physical quantities. The dimensional analysis tells us that it has to take this form. This is a much simplified form, right? It's not a function of 5 variables. It's now just a single function of a single dimensionless quantity, the Reynolds number. And so if we wanted to, we could do an experiment that we only need to change one thing, right? We only need to change the Reynolds number. We could imagine dropping a whole bunch of cones with different radii at the same, or moving cones through air at the same velocity. We could only, if we wanted to, we could just change the radius, or just change the viscosity, or just change the velocity, and we should be able to kind of trace out this entire one-dimensional function. Experimentally, this is that one-dimensional function. Here's the Reynolds number, this dimensionless constant here on the x-axis, and here's the value that this function takes on the y-axis. You notice this is a log-log plot. For everywhere from about 100 or so all the way up to sort of 10 to the 5 or 30 times 10 to the 5, a huge range of values for this Reynolds number. You'll notice that this constant, this function, this dimensionless function that governs drag is basically a constant. So when the Reynolds number gets large, and here large is something like a few hundred all the way up to a few 100,000, physics sort of doesn't care, and it behaves the same. It's sort of insensitive to this value. There's something weird that happens at very high Reynolds number, where suddenly there's a huge drop in the drag coefficient. This is like turbulent drag. This is why golf balls have dimples and why airplanes have struts to try to push them into this region. But you'll notice that over a very wide range of values, it's sort of a constant. And we might have expected that we might be in one of those regions when we evaluate the Reynolds number for our cones to be very large. In the other limit, if Reynolds number is very small, as we get to like 10 to the minus 1, it also has a simple relationship, right? This is a constant slope on a log-log plot, meaning it behaves like a power. And in fact, for a very low Reynolds number, this whole function just goes like 1 over the Reynolds number. That's just kind of like a fun fact to know. I don't, necessarily hope, neat fact, this function for very low Reynolds number flow goes like 1 over the argument. So if you kind of push that through, you'll notice that for very low Reynolds number flow, the drag force has this other form where it's actually linear in the velocity and linear in the rate linear in a physical. It doesn't go like an area; it goes like a radius of the object. What does that mean for a terminal velocity? If you happen to be in Stokes flow, this is called Stokes flow. The terminal velocity, force goes as mg. If you equate those two, you'll notice that the velocity now, sort of takes this form. If you kind of push things through, you can kind of solve, and what you discover is that the terminal velocity, if you're in Stokes flow, for an object is measured in air, is measured in millimeters per second if the object is sort of a micron in size. Okay, I feel like I'm butchering this. What I want to focus on is, okay, what did we want to say? Originally, we solved for drag force, but we ignored the viscosity. If we had included the viscosity, dimensional analysis tells us that there's an entire function that we needed to worry about. If we actually stick numbers into that function, we discover that they're very large. Generally, when the numbers, the dimensionless numbers that go into dimensionless functions in physics are either very large or very small, things are sort of simple. A lot of times just a constant. We experimentally verified that we didn't need to worry about this dependence for dropping things like cones. In so much as you're now being exposed to an interesting bit of physics, when you'll notice that if things are very small, physics is different when the Reynolds number is very small. How does Reynolds number get very small? You either need viscosity to be very large. Things behave differently in honey. And I think that's something that falling in honey is different than falling in air. That's something that we experience. But you can get similar behavior. You can behave the same as falling in honey if you fall in air, if all you do is change your radius by the same factor as the change in viscosity as you go from air to honey. And so very small things falling in air behave like large things falling in honey, because the physics only cares about their combination. This dimensionless function is all that governs the physics. And so these things kind of scale together. That, I think, is sort of interesting. If you hadn't been exposed to it before, you can actually plug in some numbers for air. you can discover that if you have a micron-sized object, its terminal velocity is millimeters per second. This is why clouds hang in the air. This is why dust floats in a room. This is why COVID is a problem. Because if I cough up micron-sized balls, those balls don't fall like cones do. They experience a different kind of physics. They fall like things fall in honey, and they fall a lot slower, and they fall with a terminal velocity of measured in the millimeters per second. So it can take half an hour for a micron-sized droplet to fall from my nose to the ground. Just kind of fun fact. Okay, before moving on, I want to leave you with one last use of dimensional analysis as like kind of a bespoke tool. And I want to mention this because I think it's actually more useful for our own jobs. So another way that you can use dimensional analysis is you can do what's called non-dimensionalization. So given any differential equation or integral, you can sort of interpret all of the symbols in the integral as if they had dimensions. Do a change of variables to make everything dimensionless and pull all of that scaling out. And you oftentimes drastically simplify formula. I want to show sort of one example of this. Let's say you forget what let's say you forgot what the normalization constant is for a Gaussian distribution. Gaussian distribution is the normalization constant is the integral of e to the minus x minus mu squared over 2 sigma squared. This is like a complicated formula, right? I mean, nobody wants to do this integral with all these symbols lying around. But like, we could ask the question, like, how does this normalization scale? Like, does it depend on mu? Does it depend on sigma, sigma squared, square root sigma, 1 over sigma? That we can figure out without doing any work. And we can figure out if we take the time to sort of non-dimensionalize this formula. How do we do that? We sort of interpret everything as if it has dimensions, right? A lot of times when we write down our formula in machine learning or whatever, we, explicitly are treating everything as dimensionless, but it sort of doesn't matter, right? In the same way that like you could imagine x being measured in length, for instance, right? You could imagine a Gaussian distribution actually taking place over some space. And if you did that, x would have to have dimensions of length. If x has dimensions of length, then mu, since it's added to x, also has to have dimensions of length. And if x has dimensions of length and mu has dimensions of length, x minus mu has to have dimensions of length, which means x minus mu squared has to have dimensions of area. And because, another consequence, since you can only add or subtract things that have the same dimension, it means that all nonlinear functions like exponential or sine or logarithm can only take dimensionless arguments. Why is that? Because something like an exponential, if you write the Taylor expansion, involves the sum of a whole bunch of different powers, right? E to the x goes like 1 plus x squared over 2 plus x cubed over 6, etc. And so whatever that x is, it has to be dimensionless because I'm adding x to its square, to its cube, to its 4th power, to its 5th power. If x had length, I'd be asking a length to an area, to a volume, to a hypervolume, and I'd be out of luck. So if we imagined x had units of length, mu would have to have units of length, and sigma would also have to have units of length, so that this whole argument is dimensionless. And so then what we can do to kind of pull this formula, pull all the physics out of this formula, all the scaling out of this formula, is we can do a change of variables, and we can change to a dimensionless variable. So we choose something like chi is x minus mu over sigma. This is dimensionless. This is a length minus a length is a length divided by a length is now dimensionless. And we just do change of variables like they teach us in calculus class. So if chi is x minus mu over sigma, then d chi, the derivative of chi, is dx over sigma. That allows us to replace this dx. It allows us to replace this argument. The last thing we have to worry about are the limits. And if x goes from negative infinity to infinity, when x is negative infinity, chi is negative infinity. And when x is infinity, chi is infinity. We make all the substitutions, and we can write this formula in this way. And you'll notice what happens is all of the physics, all of the scaling, all of the dimensions fall out. We suddenly know that the normalization of this integral scales like sigma. This whatever it is a pure number. Could be 4, 3.6, pi. In this case, it happens to be square root of 2 pi. So it's 2.5. It's the number 2.5. But the only thing that's left is a pure number. Exactly the kind of thing that like Mathematica can solve for you. It's much simpler too, right? It's easier to type this in than it is to type this in. You don't get all kinds of errors and stuff when you kind of type into that. So I just wanted to kind of mention that you should sort of, for any integral that you have to do, for any differential equation that you have to solve, if you make these, if you substitute all the variables for dimensionless versions of themselves, all of the physics falls out, all the scaling falls out, and you end up with pure math. Something that you can look up in tables, integral tables, or differential equation tables, whatever. Okay, so now at this point, I just want to kind of, that was an extended recap of things that we've done. Let's kind of keep going, and we're just going to kind of solve some neat problems, try to do the same thing over and over again. One bit of physics that we learned was things like air drag. We're going to kind of use and abuse that and try to solve problems and talk about strategies for solving problems and stuff like that. The next problem that I want us to try to solve is what's the fuel efficiency of a Boeing 747? And I think now's a good time to take a break, and y'all can kind of think about that. We've been at it for, yeah, let's take a 5-minute break, and at 12:55, we'll kind of keep going. And what's to come is we're just going to kind of talk about ways to solve this problem, introduce some other strategies, but we'll talk about fuel efficiency of Boeing 747s, fuel efficiencies of cars, cost of airplane tickets, fuel density of fuel, things like that. So I hope you come back, but we'll take a break. So you can stretch your legs. I'm also good. But if anyone has any questions, we get to questions. Alrighty. 12:55. When do we pick it back up? I mean, are there any questions or ponderings or anything?
Yeah, I find it kind of hard to kind of go from like the drag and the Reynolds number that we have to kind of fill efficiency. I'm not able to kind of make that mental connection. Like, how do I go from the fact that yes, the force kind of depends on the drag and potentially the Reynolds number, but then we need to kind of measure something like, say, miles per gallon or something like that. We need kind of to go from there to miles per gallon.
Yeah.
And should I go back to dimensionality analysis and figure out a new constant, or should I kind of figure out to extract this miles per gallon in the current constant? So I got stuck there basically.
Yeah. So I mean, I think it's a fantastic question. So yeah, let's talk about it, right? So what are the sort of like meta strategies? How do we answer a seemingly impossible question like this? And I think at a high level, the thing to start with is always just sort of try to divide and conquer, try to split that problem up, the hard problem we don't know how to solve, into smaller problems that we do know how to solve. So that's the kind of like first step. And so this sort of always works. And so let's talk for a second about just doing this. If we ask for something that's sort of difficult, like what's the volume of a sheet of paper? If I hold up a sheet of paper, what's its volume? That's something I don't know. I mean, if you ask me to guess, I have no idea. I have no idea what the volume of the sheet of paper is. But that's a problem I don't know how to solve. I can split it up into smaller problems, and then I might be able to solve. So in particular, one thing I do know is whatever the volume of the sheet of paper is, it's going to be its like height times its width times its thickness. I've taken that problem I don't know and I've turned it into 3 questions. The benefit is that I know the answer to 2 of these, right? I think I know what the height and width of a sheet of paper is, right? 8.5 by 11. Like I've dealt with sheets of paper my whole life. I don't know what the thickness is, but I can do it again. I can recurse. I can split that problem into an even smaller set of problems. What's the thickness of a sheet of paper? I don't know, but maybe I know the thickness of a lot of sheets of paper. That's something I do know, right? I buy reams of paper. I buy reams of printer paper. And so I could turn the thickness of a single sheet into the thickness of a whole lot of sheets, right? The thickness of a ream of paper and the number of sheets in a ream of paper. And if I knew those, then I would sort of know everything. I can take the one thing I don't know and I can split it up. And then anytime I have something I don't know, I sort of keep splitting it up. And eventually I can end up with like a bunch of leaves that I can make guesses for, that I feel comfortable with. In this case, I think I know the height, 11 inches, the width's 8.5 inches, the thickness of a ream of paper is like 2 inches, and there's about 500 sheets in a ream. Once I sort of know how to fill in all the leaves, I can kind of propagate things up the tree, I can get my answer. So as a sort of meta strategy, here I'm just kind of plugging in numbers, but I guess it doesn't matter. But it's 6,000 millimeter cubes roughly. Why, this is when they sort of teach you how to do interview questions or like Fermi problems generally, this is sort of like the one meta strategy that they sort of like introduce. But I think it's worth thinking a little bit like why it works. Why does it help to kind of take a problem you don't know and split up into smaller pieces? Well, for the worst part, for the first part, a lot of times when you split it up into smaller pieces, you have some sense of what the smaller pieces are. But it seems like things should only get worse, right? If I instead of trying to answer one question poorly, if I try to answer 8 questions poorly, it seems like things are going to go wrong. But the thing that saves us is a lot of times, we make mistakes. We might be a little too high on one of our estimates or a little too low on the other estimate, but generally those tend to cancel out, right? We're not usually systematically biased either too low or too high. And so when we split the problem up into smaller pieces, you can think of it almost like a random walk. If I take a random walk of many steps, the distance that I wander away doesn't grow with the number of steps. It grows like the square root of the number of steps that I take. And so there's a sort of a natural sort of cancellation that saves us, that can keep us from wandering too far away from the right answer, provided that whenever we do the split, we sort of like do make some progress in terms of our certainty. So if we go back to the question that we're interested in, what's the fuel efficiency of Boeing 747? I have no idea. So I'm going to try to take that problem and I'm going to split it up. into things that I might be able to reason about. And I heard you, Panag, talk a little bit, like what is fuel efficiency, right? Fuel efficiency is, like something like miles per gallon. It's a distance that you travel divided by the volume of fuel that you use, like a distance per volume. That's its efficiency. Okay, I've split it up into one piece. What's the distance that I travel? I could imagine making that up, but what's the volume of fuel? I have no idea. Let's divide again. What's the volume of fuel? Well, I don't really know, but there's something else that I can reason about, right? Like the energy in some volume of fuel, I know is going to be like the energy density times the mass of the fuel. So I can kind of make further progress. I don't know what the volume of fuel that a Boeing 747 uses to fly some distance, but I at least can say other things about the volume, because I know that in some volume of fuel times whatever the density of the fuel is, times the energy density, the amount of energy that you release per unit of mass of the fuel. If I knew those things, I could tell you the total amount of energy. Why is that useful? Because the total energy is something that we do have some reasoning about, right? We were just talking about drag and the energy used in drag. So the sort of twiddle reasoning really is a form of sort of divide and conquer. It's a way of sort of take those symbols that we don't know and try to come up with other things that we could equate to them that we might. So at this point, we actually we could use the other thing that we talked about, the next strategy. At this point, we could sort of be done. We whatever the fuel efficiency is, we could say it goes like a distance over a volume. The volume equates with something like the energy, and we have some sense of how energy scales. It goes like air drag. And so we could use scaling, right? You look at this whole formula, you'll notice that the efficiency goes like D over V. V goes like energy of fuel. So in total, the efficiency goes like the inverse of the energy. But we could then use scaling. We could equate two instances that we know. We don't know what the efficiency of a Boeing 747 is, but I know what the efficiency of my car is. So why don't I scale up from a car? My sort of divide and conquer twiddle reasoning gave me a scaling relation. That scaling relation allows me to scale. If the efficiency goes like the inverse of the energy, the efficiency of a car over the efficiency of an airplane is going to be the energy used by an airplane divided by the energy used by a car. And so then I know how energy goes. Energy lost to drag goes as rho A V for the same distance. So then I just need to know these ratios. What's the density of air that an airplane goes through versus the density of air that a car goes through? What's the area of an airplane over the area of a car? And what's the velocity that an airplane goes compared to the velocity of a car? These are things that I think I can estimate, right? Cars go at like 60 miles an hour. Airplanes go at like 600 miles an hour. That's a factor of 10. 10 squared is 100. The area of an airplane versus the area of a car. Car is like, you can sort of like lay down in the back of a car. Airplane has, 3 rows of 3 seats, a Boeing 747. So that's 3 people across versus 1 person across. And in terms of height, you can kind of stand in each. That gives us like another, 3 squared is 10, basically. You get like 3 by 3. It's about a factor of 10 difference in the area for an airplane versus a car. And in terms of the density of air, I don't really know. But one thing I do know is that airplane cabins are pressurized. And they're pressurized because the air outside is less pressurized. So I know that there's a difference, and I don't think the difference is too large. So it's probably a factor of a few. So I'll call it a factor of 3. So if we kind of, let's talk about that for a second, just like I was kind of making it up. But that's something that's sort of generally useful if you're just doing like arithmetic and you're only trying to get things to like with an order of magnitude. Like in school, they sort of teach us how to like round to a power of 10. But sometimes it's useful to sort of round to intermediate powers of 10. Here on the right, I'm showing a circular slide rule. So these are just, numbers from sort of 1 to 10 laid out logarithmically. The sort of distance along the thing has to do with the logarithm of the number, right? This is how slide rules work. They turn multiplication to addition by adding the log of the distances. But if you haven't played with slide rules, one thing you might not realize is that the square root of 10 is very, very close to pi. And so this gives you like an easy way to try to do fractional power of 10 type math. Like you can kind of round every number to either 1 or a few. So it's like 1 few 10, where few is like pi. So each number is either, it's either 1 or a few times 10, some power of 10, where a few is something like pi, because pi squared is something like 10. And that gives you some like intermediate resolution on estimates. So in this case, I think it's smaller. I don't think it's smaller by a factor of 10. I think it's smaller by a factor of a few. So like root 10, so like 3 or like pi. You can kind of go beyond just doing, to kind of like formalize this. If you do 1 pi 10, that's measuring everything in like half powers of 10. You could do things you could split a decade into 3 parts. And if you look at this dial, if you go like a third of the way around, you hit 2. And if you go 2/3 of the way around, you hit 5, and you get 1, 2, 5, 10. This is a very common sequence. This is how currency in most countries is done, right? You get $1, $2, $5, $10, $20, $50, $100. They do that because those amounts are roughly equally spaced in log, which means you require the fewest number of bills to make change. You might also be used to resistors in electric circuits. They have these weird values. The values that they take are actually, I think, splitting a decade into 10 or 16 values or something. I forget what the actual division is. Something that I've been playing with is something I call sexabels, which is splitting a decade of 10 into 6 pieces, because it gives you kind of roughly a factor of, it gives you like 50% efficiency to any number. So if you kind of split this dial into 6 pieces, you go from like 1 to 1.5 to 2 to 3 to 5 to 7 to 10. You can kind of round every number to the sort of nearest one of those, and multiplication in these things is just kind of clocking your way around the dial. 3 times 3 is 10, 2 times 5 is 10, 3 halves times 7 is 10, etc. It's kind of like a neat thing to play with. All right, so going back to our fuel efficiency of Boeing 747, we did divide and conquer. We split the problem up into smaller problems. Then we use scaling. We're going to try to use something that we do know to talk about something we don't. We knew that energy went like rho AV squared. That's the thing that we've been doing over and over again, drag. So we can scale from a car to an airplane. We need to know these 3 factors. Airplanes are about 10 times faster. Airplanes are about 10 times bigger. And the air up at 30,000 feet is about 1/3 of the density of air at the ground. 10 squared is 100, times 10 is 1,000, divided by a few is a few hundred. So the fuel efficiency of cars are about 300 times the fuel efficiency of a plane. So like, oh my gosh, planes are very wasteful. Maybe you should never fly, except it's not so bad because you can fit about 300 people on a plane. And so if you put 300 people on an airplane, they're actually sort of a wash. And the fuel efficiency of flying in an airplane is roughly the same as the fuel efficiency of driving down the highway, which is kind of a neat thing to know. Once we figure that out, we can actually figure out like how much does the fuel cost to fly the airplane.
Just to advertise for traveling by air, this is assuming that the car is always moving. If you factor in traffic, then airplanes are much better.
I mean, yeah, I suppose that's true. That's true. But it like also like we did earlier, right? If you're going at highway speeds, the energy use, the fuel to drive the car is dominated by air resistance. So if you're driving across the country, I think almost all of the fuel that you're going to burn is going into pushing air out of the way, because you're going to spend comparatively little time like idling at stop signs and stuff. That's not true if you're driving around the city, right? We worked out the ratio of the mass of the car to the mass displaced, and for something like driving a city block, they're comparable. And you have to worry about idling costs and frictional losses and things like that besides the air. But I think for driving across the country versus flying across the country, the fuel use is going to be comparable. And so we can estimate the actual cost of fuel. If I fly across the country at 3,000 miles, and if airplanes are going to be, 300 people in them are going to be about the same as a car, and a car is about 30 miles per gallon. If fuel costs about $3 per gallon, then the cost of the fuel to fly me across the country is about $300. That's about the cost of a ticket. That's why airlines are always going bankrupt. So that's neat.
Wait, where did we leave the factor of 300 here? We had a factor of 300 somewhere, right?
Oh, 300 times. Well, yeah. So the airplane was 300 times worse than the car, but I'm imagining there's 300 people on the airplane, so then it ends up being about the same. So
I see. Okay, that's why it's
I probably should have times 300 times 30 miles per gallon, but then divided by the 300 people.
Okay.
So then this should be $300 per person, let's say. But the cost of the fuel to fly each person across the country on a plane is about $300. So for the 300 people, it would be something like 10 to the 4, 10 to the 5, $100,000 in terms of fuel, which is a lot, but I think that's accurate. Okay, so let's keep going. What if we didn't know what the fuel efficiency of a car was? And let's see if we can kind of keep doing some estimation strategies or whatever. So if we didn't know what the fuel efficiency of a car was, we kind of pop back up our stack a little bit. We still, let's say we started over. What's the fuel efficiency of a car? We use divide and conquer. We kind of split the problem we don't know. We kind of describe it into some smaller problems. It's the distance traveled divided by the volume of fuel that we use. Yeah, I think you're right, Harvey. We need to be able to say something else. We kind of can split the problem of determining the volume of the fuel in terms of something like an energy. And we know how energy goes. Energy goes like rho a v squared. And if we kind of put that twiddle in and we don't do the scaling and we kind of work through all the math, kind of push all the equations together, we get that the fuel efficiency of a car is going to be something like the density of fuel coming from this factor divided by the density of air coming from the rho a v squared times the energy density of fuel times 1 over a v squared. And this is something that I think we can estimate. We can estimate the area of a car. We can estimate the velocity that a car goes. We can estimate the density of fuel, the density of air, and the energy density of fuel is something that maybe we don't know. And that allows me to talk about the next sort of strategy. So the only part that's remaining is estimating the energy density of fuel. And how do we get that? So the next thing I want to tell you about is I think a lot of times you actually know more than you think you do. If I just asked you what's the energy density of fuel, it feels like something you don't know. But I think you actually do. And we have to figure out how to talk to your gut to get the answer out. So how do you talk to your gut? Well, what you do, let's take a little break. Let's talk about a different question. What's the population of Canada? If you just had to guess, that's the kind of thing that I feel like I should know, but I don't really know, but I don't really feel confident about what it is. I don't know how to ask my gut the question. If I talk to my gut directly, say, hey gut, what's the population of Canada? It comes back like, I don't know.
100 million?
It's a good guess.
40.
Let's see if we can, 40, all right, yeah. People can throw out numbers.
Yeah, I thought it was like 50.
Yeah, that's roughly 40 to 50 is what I was thinking too. Yeah.
Cool. So how do we get a little bit better resolution on that? So I think a good strategy is not asking your gut what the answer is, but asking your gut for what a interval is. And why is that? Because if you imagine being Bayesian or something, if you have some uncertainty, if you had a distribution of beliefs about what the value is going to be, right near the peak, right? This doesn't, the probability changes very little as I move around the peak of some distribution. And so that's why I can't feel it. I don't feel sensitive to changes near the mean. But for something like a Gaussian distribution, the derivative is maximum at 1 sigma. That's where the density is changing fastest. And where it's changing fastest, where the greatest change in your sort of belief, is where I think you can kind of be more sensitive to how it feels. And so the strategy is, instead of asking your gut a straightforward question, like what's the answer? Instead, what you should do is you should try to ask your gut for what value feels too small. Like where would you be surprised if it was less than? And ask your gut what value feels too high. What would you be surprised if it was higher than? And then try to find the middle. If we're talking about positive quantities, this whole thing is going to be not a normal distribution, but like a log normal distribution. So we're going to take geometric means rather than arithmetic means. But the idea stays the same. For a Gaussian distribution, the maximum change in the slope is happening at plus and minus sigma. That also, you know, a 1 sigma boundary corresponds to like a 68% interval, meaning each one of these tails is something like 1/6 of a probability. And I'd say that that corresponds to like moderate surprise. Moderate surprise means you'd be moderately surprised if your friend says, I'm going to roll a 1, and they roll a 1. That's like, that's moderately surprising. So now what we do is I ask my gut. If somebody told me the population of Canada, I start walking my way sort of up the scale, and I'm going to do it with like 1 through 10. So I'm going to ask my gut, hey, gut, what about 1 million people in Canada? My gut goes like, that's too small. Like, that's too small. That's a large city. Canada's bigger than a large city. Then I say, hey, gut, what about 3 million? And it's like, you know, that feels small. That's a big city. That's like Chicago. Canada's bigger than Chicago. What if I say 10 million? Now my gut's like, oh, I would be mildly surprised if somebody told me Canada has less than 10 million people. That it feels like a sort of an edge for me. This is a personal thing, but for me, 10 million, I'd be mildly surprised if somebody told me Canada had less than 10 million people. So then I keep going up. 10 million, 30 million, I don't know, sure. 100 million, you know what? I would be mildly surprised if somebody told me Canada had more than 100 million, because I know that the US has like 300 million, and I know that Canada is smaller than the US. So once you get to like 100 million, I'm like mildly surprised, because once you get to 300 million, I know that it's not bigger than that. And so I can feel it a lot more. Like I can feel my gut telling me, you know, those edges sort of more viscerally than I can the middle. And then all I have to do is take the mean. Since we're working with positive quantities, we're working the log thing, I take the geometric mean. So if my edges were 10 million and 100 million, I multiply them together, I take the square root. Square root of 10 is a few. Square root of 10 times 10 is, 10. So I get a few 10 million, I get 30 million. That's my guess. It turns out Canada actually has 37 million people. So we're sort of within a factor of 20% or so of the right answer, which is pretty remarkable and something that if you had just asked me, I think like people are throwing out like 100 million or something, I probably would have just like thrown out a number and I would have been further off. Okay. Yeah, sure. What's the population of Zimbabwe? Am I supposed to be the one demoing it? Is everyone supposed to be demoing it? Why don't we all do it? So here, I'll start reading
maybe
off
we can all do it as a class.
Yeah, let's all do it. So we'll start low, Zimbabwe. We'll start at 30,000. Okay. So everyone just kind of keep track. I'll go up by powers of 3, and I want everyone to kind of write down when they feel like when they feel mild surprise if it was too low, and then mild surprise at the high end. So 30,000, 100,000, 300,000, 1 million, 3 million, 10 million, 30 million, 100 million, 300 million, 1 billion. And I can probably stop. So things have disconnected.
My mild surprises on the lower end will be like 1 million.
For me, so sorry, what did you?
I think that for me, like Zimbabwe, like on the lower end, I'll be mildly surprised if it was less than 1 million. And then on the higher side, probably greater than maybe 30 million. I'll be mildly surprised. Yeah.
30 million. All right.
Yeah.
So you went from 1 to 30. So square root of that is square root of 3. 3 times square root of 3 is something like 5. Let's say 5. Or
5 million.
Yeah, 5 million. All right. I think I know less about Zimbabwe. I went from about 1 million to 300 million, so I have a wider range. But that puts me at something like 50 million for my middle. All right. So I will look it up. Population of Zimbabwe.
It's 15 million. I just looked it up.
15. All right. Cool.
It's pretty good.
Yeah. For something I had no idea about, to get within a factor of 5 is pretty good. So, okay. so let's return to our original question. What's the fuel efficiency of a car? We sort of did our divide and conquer in our twiddle thing. We broke it down to this form. We had all these terms, and there was the energy density of fuel. I don't know, but we're going to try to talk to our gut. We're going to phrase it a little bit differently. What's the energy density of fuel? We're not going to ask that directly. We're instead going to ask what's the energy density of butter. Fuel's a hydrocarbon, so is butter. So what's the energy density of butter? Let's imagine you had 1 gram of butter. How many calories is that? How many calories is 1 gram of butter? I guess I don't really know, but I would say I'd be surprised if it was less than 1 calorie, and I'd be surprised if it was more than 100. So that puts me at about 10. About 10 calories per gram. A food calorie is a kilocalorie, and it looks like fat actually has 9 kilocalories per gram. So yeah, I think we're right on the money. We stick all these numbers together. Density of fuel. Fuel is like water compared to the density of air, and water is 1,000 times the density of air. We talked about that last time, so we get a factor of 1,000 there. The energy density of fuel, if fuel is like butter, that gives us 10 kilocalories per gram. We need to turn that into sort of SI type units, so we need to go from gram to kilograms. That gives us 1,000 grams per kilogram, and I happen to know that there's 4,000 joules per kilocalorie. That's, I don't know, something to look up. And then we have to estimate these terms down here: area and velocity of a car. Car, I'm saying, is about 2 meters across and 1.5 meters tall, and cars go at about 30 meters per second, or about 60 miles an hour when going down the highway. And if you kind of do all that math out, you approximate things, cancel all the factors, you get something like 10 to the 7 that survives. I guess we can kind of do it out. Here's 10 to the 3, 10 to the 4, 10 to the 5, 6, 7. 2 times 3 halves is a 3. The 3 and the 4 cancel. This is a few times 10 squared, gives us 10 times 100. This is another factor of 1,000. The factor of 1,000 kills that 1,000, more or less with the 10 to the 7 we had before. The interesting thing here about fuel efficiency is if you look at all the units, what are all the units here? We had a dimensionless density ratio. The kilocalories kill the kilocalories, the grams kill the grams, the kilograms meters squared per second squared, so we kill the joules. And this whole quantity, fuel efficiency, is measured in per meter squared. Sort of a weird unit. Our answer was 10 to the 7 per meter squared, which is about 10 per millimeter squared. And that's a weird unit, but it actually has an interpretation, which is neat. What it's saying, in America, we measure fuel efficiency in like miles per gallon, but in Europe, they measure it in gallons per mile, right? Which is maybe makes more sense. If we flip this, instead of being miles per gallon, it was gallons per mile. Gallons per mile has the units of area. And what we notice is that for our car, our estimate was that it would be about 0.1 millimeters squared in sort of gallons per mile. What is that area? That area is actually the area of like the fuel tube that your car would poop out if it was pooping out the fuel that it was using. As your car drives down the highway, the amount of fuel that it uses is the fuel that would fit in a little 0.1 millimeter cubed rope that it behind it. But that's our answer. We estimated the fuel efficiency of a car. We broke it down to the pieces. We estimated the pieces. You put all the numbers together, and then if you do the final conversion to miles per gallon, we get an estimate of about 20 miles per gallon using just all of our raw numbers. And for my money, that's a pretty good estimate. That's fuel efficiency of most cars, certainly within a factor of a few. And I think that brings us to the end. That's more or less all I wanted to tell you. I wanted to end with the fuel pooping car. So that's it.
So
Any questions?
I have a question. Yeah, question. Yes. So where did we use the dimensionality kind of analysis here? Is it to just kind of arrive at the fact that energy varies with respect to the rho AV square? And that's where the dimensional analysis was kind of used in the first place. And then you kind of go to either scaling or kind of something like this. Is that right?
Yes. In an alternate universe where we hadn't first worked out how air resistance worked, if you if we started with this question, what's the fuel efficiency of Boeing 747? In an alternate universe, you would have tried to divide it up into smaller questions. You would have done things like, what is fuel efficiency? It's the distance divided by volume. The volume might go like the energy, and then you'd have to estimate what the energy fuel use was. And for that, you'd have to figure it out. And the first time that we figured that out by doing dimensional analysis. You don't have to use dimensional analysis, but it's a tool, and it's a tool for things like that, where you have a physics question. How does the energy of fuel use depend on other physical quantities? If you get to the point where you have some physics quantity you're interested in and you don't know how it depends on other things, the tool to use, and the tool that we used the first time, was dimensional analysis to figure out how energy of fuel use depended on the other quantities. And that's where we got the rho AV squared. So you can imagine an alternate universe starting with this and just doing divide and conquer, breaking up into problems, getting to this point, doing dimensional analysis to figure out how energy depended on the other quantities. And if you didn't do the scaling, you stick in all the numbers, you estimate some things, you plug in all the numbers, and you can get 20 miles per gallon, which pretty good at the end of the day.
Cool.
So yeah, dimensional analysis, it's anytime I suggest it's because it's simple to try. So anytime you have a thing that you don't know how it depends, I suggest trying it out. So you write down the thing that you want to know, you write down its dimensions, or you figure out its dimensions, or you look up its dimensions, and then you start making a list of things that you think it might depend on. You write down their dimensions, and you start forming dimensionless constants. You see how many there are, how many are left over, and then you start plugging in numbers, figure out the ones that are very big or very small, or see if you can kind of tell stories for yourself, start doing twiddle type things, if you could figure out where those factors are coming from or what physics they might be describing. And before you know it, most of the time, you can kind of figure out how things scale. And a lot of times you can actually get something that looks like a scaling relationship. And then as long as you have some experience of some other version of the same problem, you can solve it. Like the first time we did the airplane, we did it by knowing what car fuel efficiencies were, and we just scaled it up. Otherwise, you at some point have to estimate numbers, and you can either look up numbers or you can talk to your gut. And yeah. So there we go. I encourage you again, if you enjoyed this, or if you thought that some of this stuff sounded cool and I was going way too fast and didn't do it any justice, then I very much encourage you to read these books by Sanjoy Mahajan. Very good, and describe most of the, these problems and others, and all kinds of fun things and all kinds of neat things to work on. So.
Do you prefer one of the books or others? Yeah, exactly. Same as Alex.
Yes. So this one is shorter. This one is longer. This Street Fighting Mathematics is full of more general purpose things. It's less physics and more just like mathematics, Street Fighting Mathematics, how to estimate integrals and lumping and things like that. The Art of Insight and Science Engineering is actually more physics-based. So in the sense that, but without having to do physics, in the sense that he'll show you sort of twiddle arguments for things like how does temperature work, how does diffusion work, how do things cook, and how does drag and flight and fluid dynamics and waves, and he'll talk about sort of lots of sort of phenomenon in physics, but in the kind of way that we were talking about it here. So if you want to do more physics, look at this one. If you want just sort of like mathematical tricks for estimation and stuff, and maybe more for our own jobs, I would read Street Fighting Mathematics. That's also shorter. Anything?
Yeah, one of the things that I think is like kind of unfortunate, we were talking about this earlier, Alex, was that like the sort of reasoning that you learn in these courses, I feel like is very useful for dealing with just general, like the world, like these sorts of questions that you were saying, what is the fuel efficiency, other questions you can imagine. One thing that I think is kind of unfortunate is that I haven't really found any good applications of these sorts of methods in our own field. So it would be cool to brainstorm with people, where can we apply this sort of reasoning to just like do back of the envelope calculations in ML.
Yeah.
Yeah,
so,
something like that.
Yeah. So part of the problem is, our own field makes the mistake of lots of other fields in which we sort of write down all our formulas and treat all the things as being dimensionless. One place where I
Yeah.
have seen somebody talk about it is in the Ada Delta paper. In the Ada Delta paper, there's this section 3.2 where he talks about how silly like SGD is in the sense that, if you're actually going to compute a derivative, like we said, like, if you do sort of Twiddle type stuff, when you compute the derivative of a function, if you pick up the inverse units of the thing that you take the derivative with respect to. And so SGD sort of doesn't make any sense unless the learning rate has dimensions of sort of like a square
totally agree.
thing. And I mean, that's okay. It could have that dimensions, but the fact that we sort of don't recognize that means that a lot of the like having to change the learning rate when you scale the inputs and stuff are things that we just sort of have to deal with because we sort of weren't aware of it when we went in. But I maybe part of why I'm giving this is I kind of want to encourage everyone to kind of take another look at what we are doing and see if there's other opportunities where we're sort of forgetting putting, I think, I wish I had more examples to point to where putting units in ML things helped. I am suspicious that there are opportunities in which it can. And part of why I was motivated to do this for this audience is I want to encourage everyone to, even in our own work, start thinking about the units that things have and see whether that simplifies or resolves some of the problems.
Yeah, the comment wasn't like about this lecture. The comment was just like saying basically that like if anyone is interested in sort of brainstorming, or we'd be happy to talk. That's all I was saying.
Yeah.
Totally.
Awesome.
Yeah.
Me too.
Cool. If there are no more questions, we can stop the recording. So yeah, thanks Alex. Thanks for the awesome lecture. I'm going to stop the recording.